Hello everybody and welcome back to Geo 101, and in today's video we will be going through a past paper question. This question is from the Geography CSEC past paper May-June 2016, and it comes from section B. It's question 2. So without further ado, let's get into the video. So our first question asks us to draw a diagram to show the formation of a spit. Now, before we could even draw the diagram, we first need to know what a spit is and how it's formed. So a spit is a narrow finger of sand or pebbles that juts out into the sea from the land. So here we have an image of a spit, and as you can see, we have the land, and then we have the narrow finger of sand or pebbles. That is our spit. So if we zoom in here, we can see the points where the land stops and where the spit begins to form. So this is what a spit looks like. Now, into how a spit is formed. So in order for a spit to form, we need to have a coastline, we need to have prevailing winds, longshore drift, change in wind direction, as well as a river estuary, which I would explain later on, right? So we have the coastline here, and along the coastline, we would have something called a headland. A headland is basically a part of the coastline that juts out at sea. Now, with the prevailing wind, what happens is we have wind that is blowing towards the coastline, and it is moving the sand and sediments that's on the coastline. The wind is moving it and carrying it down the coastline, and that is a process called longshore drift. When these sediments that is being carried down the coastline, so the longshore drift, when it reaches the headland, instead of it continuing to travel down the coastline, it goes out at sea. And that is how the spit is formed. The sediments continue to go out at sea, and it accumulates and builds up and up until eventually the sediments reaches above the water's surface, and you can see it over the water. Now, the part with the change in wind and wave direction come in the formation of the hook that we see on this spit. So for example, with the image here, where you see the hook, this is formed by a change in wind and wave direction. So the change in wind or wave direction, it changes the direction that these sediments are traveling in, and that is what causes the hook. Now, the river estuary comes in the formation of something called a salt marsh. So for a salt marsh to occur, it needs to have the spits, the coastline, and a river estuary. A river estuary is also the point where a river meets the sea. So a salt marsh is basically a protected area. It's a coastal grassland area, and that is usually regularly flooded by sea water. Basically, it's behind the spit, and is protected because the spit here, because it's above the surface of the water, it protects it from the waves, but that doesn't prevent waves from coming in and flooding the area. It is not completely open to the seawater because of the spit that is in front of it here. And it's an area where vegetation grows, vegetation that is able to grow in salt water, like certain types of grasses or weeds grow in this area as well. Now we're going to go into how the diagram on how this spit is formed. So just as I explained earlier, we start off with the headland. Sorry, not the headland, we start off with the coastline. So we have a coastline here. We include the headland. So this is our coastline here. So coastline. Right. As I explained earlier, we need to have prevailing winds that is blowing towards the coastline. So you can just draw some arrows showing that the wind is blowing in this direction. Right? So we have a prevailing wind that is blowing towards the coastline and causing longshore drift to occur. So now it's time to draw on longshore drift. We draw sand and sediments that is moving along the coastline. And we are labeling this. Longshore and so that's the longshore drift, and it's gotten to the headland now, so we just label our headland. Right, so it's our longshore drift has gotten to the headland, and now instead of it continuing to travel down the coastline, it goes out at sea, forming this spit. So this here is our spit. Now to show how the curve is formed or the hook, we need to include our change in wind or wave direction. So get our arrow again. Nice. And that is what forms our hook. So we just include our hook piece here. So this is our spit here. And now we have to include how the salt marsh is formed, which is basically the area in between the spit, the headland, and the river estuary. So now we can include our river estuary, and I could just show the area where the river estuary is in relation to the salt marsh. Right here. And we nice. And then we can now include our labeling for our salt marsh. And that is our diagram for the formation of a spit. So, and now we don't forget to include our title for the diagram. So we see diagram showing the formation of a spit. Nice. And that is it. That is our diagram. So now, question 2, define the term soil creep. Oh, before we move on to question 2, so you could choose to use this diagram here as an example for when you have to draw the diagram, or you can use the one that I drew just now. So question 2, B, sorry, define the term soil creep. So soil creep is an extremely slow downhill movement of soil. While it is too slow to be able to see it happening, you see evidence of the process on hillsides. It is different from a landslide that is a sudden downslope movement of part of a hillside. Now, soil creep, like we said, is not to be confused with a landslide, because a landslide is sudden and all at once, while soil creep happens gradually. It's the gradual movement of soil over time down the hill. So a good example of soil creep would be if you ever saw a house being carried away by the land, that is an example of soil creep, because the soil is moving and it's carrying the house with it, and it's happening slowly over time. So state 2 indicators that soil creep is occurring on a slope. So the first one is that terracets can be seen. Terracets are long, low ridges that follow the contour of a slope when the soil moves down. The second indicator is that you can see tension gashes in the road. So the first thing, the terracets can be seen. Terracets, as we read by the definition, are long, low ridges that follow the contour of a slope. So if we zoom in here, the soil is moving down the slope and is causing these contours in the land, and this is what we refer to as terracets. Then now we also have the tension gashes, and this is an image of what it looks like. It's just these gashes that would appear in the road. So here's an image here of the tension gashes, and here is another image here. Right? Let me see another image here. Although the question asks us for 2, we'll give more than 2. Another indicator of soil creep is that telegraph poles appear inclined as they are moved from their original position caused by the moving soil. So if you see the telegraph poles moving and they're leaning, that is an indicator that the soil below it is moving, which is an indicator of soil creep. Here's also a diagram that you could use for reference, showing the different indicators of soil creep. So we have a telegraph pole that we mentioned earlier. We have a tension gashes in the road as well. And we have a terracets that are shown going down the hillside. There are also other indicators. We see the base of the tree turn down slope is another indicator as well. And over on this side of the diagram, it's explaining how soil creep works. Basically, how soil is that when it gets wet, it expands, and when it's dry, it contracts. So when we have soil that is on a hillside, when it's wet, it expands, and when it contracts now, there's space left from where it had expanded, and now that causes the soil to be able to move because there's no extra room for it to move, and that is what causes it to move downhill because there's no this extra space for the soil to move. And that happens over and over, so expanding and contracting, expanding and contracting, and because it's on a hill, gravity is moving the soil, and that is what causes the soil creep, right? So okay, so the third part to part B of question 2 asks us to list 4 human activities that contribute to landslides in the Caribbean. So the 4 human activities that we have here that contribute to landslides in the Caribbean are buildings, removal of vegetation, excavation, and mining. So buildings increase weight on a slope and add to the downward pull of gravity. Removal of vegetation. What happens with vegetation is that the roots of plants and trees, they bind the soil together. So when you remove vegetation and you remove the roots, you disturb the soil and the soil structure, and it could contribute to a landslide. Excavation as well. The digging in the soil as well as undercutting the soil or a slope makes it unstable and could cause landslides, as well as it's the same thing with mining. You're digging into the soil and you're making it unstable, and it could trigger a landslide the same way. In a case with mining, it would also have to be if they are mining somewhere on a hillside. That's usually where landslides take place because gravity has to pull the soil or the land down, and that can only take place on a height or on a hillside. So the next question is explain how earthquakes occur at transform plate boundaries. Now, there are 3 different types of plate boundaries. They are convergent, divergent, and transform plate boundaries. Transform plate boundaries is where 2 plates are sliding alongside each other in opposite directions at different speeds. So how an earthquake takes place at a transform plate boundary is basically when you have the 2 plates sliding against one another, it causes friction, and the plates kind of get stuck together, and when it's finally released, the point where it's released, it sends up seismic waves, so it releases pressure in the form of seismic waves, and these waves then make their way to the surface, and that is what we feel as the earthquake on the surface. So again, because the plates are sliding smoothly against each other, it causes friction and tension along the edges of the plates. When the plates finally break free, it can send out seismic waves from the focus. The focus is the point at which the 2 plates, it broke free. The focus is the point at where the seismic waves are released. These waves then eventually reach the surface, and that is what we feel as the earthquake. The point at which the seismic waves reach the surface is known as the epicenter. So, account for the formation of 4 mountains and volcanoes at destructive plate boundaries. So, destructive plate boundaries is another word for convergent plate boundaries. Basically, these are plate boundaries that are colliding together. So we have transform, which are sliding alongside one another, and we have divergent, where they are moving apart. Convergent or destructive, as the question has it here, is where the 2 plates are coming together. Now, a fall mountain forms at a convergent plate boundary, and it's basically when the 2 plates collide, sediments and continental crust, it buckles and folds, and the result is enormous amount of rock and debris, and that is what we get as the full mountain. So you can think of it as literally like two rocks that you have, and you smash them together, and you continuously keep doing that, and eventually the rocks will break apart, and you're going to be left with the debris of the two rocks that you have that were colliding together, and that debris is what you get as a full mountain. So for example, the Himalayas is a huge full mountain that we have on Earth, a full mountain range, and it's formed through the collision of the Indian plate and the and the Eurasian plate. So the formation now of a volcano is also formed as a convergent plate boundary, and what happens is we have two plates that are coming together, and what happens, instead of them colliding in the instant like a full mountain, they collide, but one plate is subducted or sent back into the earth. This plate is usually the heavier plate, which is the oceanic plate. So we have two types of plates. We have continental plates and we have oceanic plates. Oceanic plates are a lot heavier. So when the two plates collide, the oceanic plate is the one that is sent back into the earth. And it's a process known as subduction. And when the plate gets sent into the earth, the rock, because remember, plates, it's rock, it's crust, the plate melts, it begins to melt, and that molten rock or lava makes its way up to the surface. And when it reaches the surface, the magma comes to the surface and it cools, and that process continues to happen, and the magma rises and cools, and it builds up and up until eventually you get the volcano shape that you know. So this diagram should be able to explain it a little better if it is not following. So basically we have the two plates here. We have the oceanic plate and we have the continental plate. And like I said, the oceanic plate is heavier, so that one is subducted or goes back into the earth, and it begins to melt again, and that magma rises up to the surface and breaks through the crust, and that is what forms the volcano. So when it breaks through the crust, it cools, and that process continues to happen over and over and over until it builds up and up and up, and that's what you get as the volcano.